Welcome. In the last session, we defined the spinodal line. The spinodal line was defined as the point where the second derivative of the free energy with respect to composition becomes 0. That is the curvature of the free energy versus composition curve. Wherever it becomes 0, for that temperature you will note those points down in the phase diagram, and if you keep doing it at all temperatures, then you get the spinodal line. So, we also said that the physical significance of the spinodal line is that it separates regions which are metastable from regions which are unstable. So, we are going to make this a little bit more quantitative. We are going to derive and show that the region where things become unstable is the spinodal region. Okay. So, that is what we are going to try and do today. So, for doing that, let me start with some thermodynamic property. We will later say that the thermodynamic property is actually the Gibbs free energy, but that let us do it later. So, for now let us take a generic thermodynamic property which is represented by the symbol capital X. As a function of composition, let us say that it has some very complicated relationship. Okay. So, the property versus composition diagram. Okay. So, this is composition and this is the property. So, let us say that it has some complex expression, something like this. Okay. So, now I am going to choose a particular composition, let me call it as x naught, and I am going to choose another composition. Let us say that that is some composition here, for example, or some composition here, for example. Okay. So, let us consider this and let us call this composition as x prime, for example. Okay. So, this derivation is again from the article of Hilliard. So, we are going to start from this point. Okay. So, I take a solution which is at the overall composition x naught, and let me produce some x prime from that composition. If I ask you what is the change in the property x when you make this x prime from x naught, and let us assume that the amount of x prime that you are producing is so small and x naught is solution is so large that solution composition remains at x naught, then one would think that the naively the free energy difference will be given by this quantity. Okay. And let us say that that is some delta x prime. Okay. But in a system like this is not actually the change in the property x, because you are producing composition x prime from x naught. This will be if the system is open, that is if you can take material from outside and produce, then that is when this will be true. But we are dealing with a closed system, right. In such systems, you have to account for the fact that you are dealing with a composition x naught, and when you add or remove A and B atoms from this composition, then you are going to have changes in the property which are known as partial molar properties. If this was free energy, that partial molar property would have been the chemical potential, but we are talking about a generic property. So, there is a partial molar property which is given, as we know, by drawing a tangent to that point, and the partial molar property for this composition x1 is here. So, let me denote the partial molar property by putting a line over that, and similarly x2 bar of x naught will be the partial molar property for this composition x naught, because this is where it is cutting the y axis for the component 2. So, these are A and B. So, this could be x bar A and this is x bar B, for example. So, we are dealing with a binary system. So, this partial molar property has to be accounted for when we are trying to see what is the change in the property x, because we are trying to form small portion of x prime composition from x naught composition, x naught is the solution. If we want to do that, then we can calculate that quantity. So, let us try and calculate that quantity. That quantity is calculated as follows. So, first we want to write the delta x, the change in property, that is for transferring. So, let me call this as delta x a. So, delta x a is given by x prime times x 2 bar x prime minus x 1 bar x naught, sorry, x 2 bar x naught. Okay, so, what does this represent? This represents the change in x for transferring x prime mole of component 2 from a material of composition x naught to material of composition x prime, right. So, this is what we mean by the partial molar properties. When I am trying to take x prime mole from a material of composition x naught, and if I add it to a material of composition x prime, the free energy changes associated with this per atom changes associated in transferring the B atom is actually given by this quantity. So, the difference multiplied by the total number of atoms that you are transferring. So, that will be the free energy change associated with that. In a similar fashion, let me call del x b, that will be given by 1 minus x prime, because remember this is a binary alloy. So, if it is x prime, this is 1 minus x prime, then x 1 bar of x prime minus x 1 bar of x naught. This will be the change in the property for transferring. Now, we are transferring 1 minus x prime mole of component 1 from a material of composition x naught to a material of composition x prime. So, the total change in the property associated with producing material of composition x prime from a solution of composition x naught is basically the addition of these two. Okay. So, if we then write the total change in the property, so that looks like this. So, the total change in property delta x is nothing but the delta x a that we wrote and the delta x b that we wrote. That is nothing but x prime x 2 bar of x prime minus x 2 bar of x naught plus 1 minus x prime into x 1 bar of x prime minus x 1 bar of x naught. Okay. So, again to go back to the initial picture we had. So, I am trying to take a solution of composition x naught, I am trying to produce some quantity of material of composition x prime from here. The amount that I am producing is so small that this overall composition remains the same. If it is an open system, the difference in the property x because of this will be just given by this difference, but we are in a closed system, which means if you take or put A or B atoms at this composition, the change in free energy is given by the intercepts along the y axis for the tangent that is drawn at this point. Similarly, for this point you have to draw a tangent, and where it cuts, that will determine the changes in the property per atom that you add. So, that has to be accounted for when we are trying to calculate this change in the property x when you are trying to do this. And so, if you take the definition of partial molar quantities, we find that you can write that expression, and that expression looks something like this. Okay. So, it consists of two parts. One is for taking the component 2 from a composition of x naught and putting it to some composition x prime, and that is x prime amount, and 1 minus x prime amount of component 1 if you take from a composition of x naught and put it into x prime. So, this is the quantity. So, there is a little bit of algebra here. So, let me simplify this and write this expression. So, this expression can be simplified as follows. So, let me take x prime and let me take x2 bar of x prime plus, so this is the term that I took, and then this term. So, this 1 minus x prime times x1 bar of x prime. Okay. So, I multiplied this, that is the first term, I multiplied this, this is the second term. Now, for the next term I am also going to write this. So, x naught times minus x naught times x2 bar of x naught minus 1 minus x naught terms x1 bar of x naught. Okay. So, what did I do? Instead of multiplying x bar and 1 minus x bar, I have instead put x naught and 1 minus x naught, which means there is some more terms that we need to add to make sure that this goes back to that expression. What is that? X naught minus x prime times x2 bar of x naught minus x1 bar of x naught. Okay. So, this x bar and that multiplied that term, and this 1 minus x bar when it multiplies those terms, they are all going to come here. So, we are going to get this expression. Okay. So, why are we writing it like this? To simplify the expression. What does the expression simplify to? You can see that this delta x is nothing but, what is this quantity? This is nothing but the property x at the composition C prime, right. What is this? This is nothing but the property x at the composition C naught, and what is this? This is nothing but x prime minus x naught, because remember x2 bar minus x1 bar, what is this quantity? So, you are taking at the two y points and the difference, and the composition axis goes from 0 to 1. So, this part can be written as dc by dx at, so sorry, dx by dx at composition x naught, right. So, this is nothing but the slope at x naught, if you take, that will tell you the x2 bar x prime is basically where the line cuts the y axis for the component 2. This is nothing but where the line cuts the y axis at the pure A, where x equal to 0. So, if you take the common tangent, the tangent at the position x naught, where it cuts the two lines. So, let me go back here. So, if I draw a tangent here, so this will be x2 bar of x naught and this will be x1 bar of x naught, right. Sorry, so this will be x prime. I already have x1 bar of x naught and x2 bar of x naught here. So, if I take for x naught the tangent, where it cuts is x2 bar, where it cuts is x1 bar. So, if I take this difference and divide by this, because this goes from 0 to 1. So, basically it is the slope of this curve at this point. So, that is what so we have done. So, x2 bar x naught minus x1 bar x naught is nothing but dx by dx at the point x naught. So, I have switched the signs, x1 minus x naught minus x prime, I have made it x prime minus x naught. So, there is a minus sign. Okay. So, this is the delta x. Okay. Now, what does this correspond to? As you can see from this figure, the quantity that we have derived, that delta x that we have derived, let me write that expression, delta x equal to x of c prime minus x of c naught. Okay. So, that is this difference minus x prime minus x naught dx by dx at x naught. In other words, this quantity that we are having is nothing but this point where you are trying to calculate x prime, this distance, that is the delta x. Okay. So, that is why I marked it as delta x prime. So, when you take from a solution of composition x naught some material and make a composition of x prime, the change in the property x is given by basically you draw a tangent, and from the tangent point to the composition that you are making, at that point you find out how much is the property difference, that is delta x. So, that is what this quantity is, right. So, this will be the expression which is the difference between the two property values will be just for an open system, and for a closed system this is what it is going to be. So, this is the geometrical interpretation for the quantity that we have calculated. Okay. We have derived that this should be the quantity. Okay. So, in the next part, next segment of this lecture, we will see what this means. Okay. So, we will do a simple Taylor series expansion and we will try to understand what this means. Thank you.